So today continuation of that semiconductor devices. Okay. So here in previous class start here how the band is look like. Okay. And now today we discuss the energy band diagram. Okay. So starting energy band diagram. Energy band diagram. Okay. So here we see that there is a conduction band here band and that is that lowest part of the conduction band EC and that is valence band and that is the highest part of the valence band is called EV. Okay, that's the lowest part of the conduction band, that's the highest part of the valence band, and in between there is a band gap or energy band gap or energy gap is called EG. Okay, so energy. Okay, now here you see that that's a basic diagram. Now if I put here diagrams now look like, suppose I say that that's the conduction band and that's the lowest part of the conduction band is called EC and now the valence band here VB and that's the highest part of the valence band EV. So here you see that this diagram that the energy gap EG is equal to 0. There is no energy gap here in that diagram. So we know that from previous class that the valence band always filled by valence electron and conduction band is empty band. Okay, empty band. And now here in that diagram the all filled electron valence band electron are in conduction band. So all electron share or valence band electron share with conduction electron. Conduction band. When electron are in conduction band, so they easily conducted and some charge moving, so we get some current here. Okay, so they get conduct and we get current because that conduction electron and these valence electron now are in conduction electron. So valence electron are in conduction electron in that diagram. Okay, so here the energy gap 0, we always get current. Here we always at any time, any situation, we always get current. So that example is a metal. Okay, we know that metal is a good conductor of electricity because there the energy gap is 0. So all valence electron are also in conduction electron and that electron conduct electricity. Okay, so that's the basic diagram of metal, energy band diagram of metal. That's the energy diagram, energy band diagram of metal. That's the energy band diagram of metal. And we know that metal is a good conductor of electricity. Now, what is the band diagram of insulator? So that's the conduction band and that is that valence band and that is the lowest part of the conduction band is called EC and that's the highest part of the valence band EV and that's this gap is energy band gap EG or you can say that energy gap EG. Here you see that this energy gap is greater than 3 electron volt. Okay, so we know that the valence band are filled by electron. Okay, the electron, and now that electron try to jump this EG to reach conduction band. Actually, that's the look like impossible here because that energy gap is very high, and this electron need too much sufficient energy, need a more energy from that overcome that band gap. So that is like impossible here. Okay, so that's almost impossible here. So that's why the electron in valence band do not jump into conduction band. So conduction band here always empty. Always here empty at any situation, and valence band is filled. So there is a no conduction electron. So no conduction electron here. Conduction electron. So there is a no conduction electron. So means no current here. Okay. So that means no current. If there is a no current in that situation, if you get a no current here, that is an example of an insulator. Insulator. Insulator is a bad conductor of electricity. Bad conductor of electricity. Why? For with the help of band diagram, we say that the energy gap is large. Eg is so large, or say that too large to electron jump from valence band to conduction band is look like impossible. So that's why we say that there is a conduction electron is impossible. So there is no conduction electron. So no conduction electron means, so no conduction here. So no conduction means no current. So that's why metal is a bad conductor of electricity. Okay, but in between insulator and metal we get a semiconductor. That's our discussion. Okay, and band diagram of semiconductor. Okay, and you see that that's the call, suppose EG. Sorry, that's called semiconductor. If I say that's that CB conduction band, and the lowest part of the conduction band is called EC, and here we see that a valence band, and that's the highest part of the valence band is EV, and that's the energy gap EG, and this energy gap is say less than 3 electron volt. Less than, for silicon there is a very less value here for pure semiconductor. So Eg is less than 3 electron volt. So electron are jump from valence band as a energy state, obviously valence band to conduction band is possible. Okay, at room temperature. At room temperature means 300 Kelvin, electron easily jump valence band to conduction band. Okay, and we get some current, when electron in conduction band, so that electron conduct electricity. Okay, so valence band electron do not conduct electricity. Okay, always conduction band name suggests that conduction band means they are filled with conduction electron, and that electron easily conducted. Okay, so these electrons flow, and the mainly charge carrier. They are mainly the charge carrier. Okay, so you get some current. But if you say that is a temperature is 0 Kelvin, so temperature at 0 Kelvin you do not get current. So current equal to 0. Then semiconductor treated as a insulator. At a 0 Kelvin, semiconductor behave as insulator. Okay, but at T greater than 0 Kelvin, a semiconductor is as a metal, or say the good conductor of electricity. Good conductor, not too much good conductor electricity, but also say that good conductor of electricity. Okay, that's the band gap of semiconductor is very important. That is not as high as a insulator, but at not zero as a metal. Okay, but in between that lie. Okay, so that's why a semiconductor is very important. Sometimes it behave as an insulator, sometimes it behave as a metal, or say that's a conductor of electricity. There is some parameter here at temperature parameter. If we say other parameter also here, but we now put a temperature factor. We say temperature, there's a 0 Kelvin behave as a insulator. Okay. Now we discuss a pure semiconductor or intrinsic semiconductor. Here we study pure semiconductor. Pure semiconductor, another name is intrinsic semiconductor. So, both the name are same. What is pure semiconductor? What is a impure semiconductor? So first we study what is a pure semiconductor. Pure semiconductor is look like silicon, germanium, whose have 4 electron in last cell. They are a pure semiconductor, also called an intrinsic semiconductor. Like silicon, there is a 4 electron in last cell, 1, 2, 3, 4, and there is another silicon here. They also the 4 electron, 1, 2, 3, 4, and here also silicon, 1, 2, 3, 4. Here also silicon, 1, 2, 3, 4. Actually, this diagram look like a lattice structure diagram or a crystal structure diagram. This is a crystal diagram. Okay, look like a 3D diagram. See that. There is an electron, and each corner of this cube has electron, and they are not end here. Actually, they are continuous. Okay, they are continuous. And top side we get electron. Here we get some electron. Where we suppose here we get some electron. Here we electron. Okay, and these are here also electron. Okay, and you visualize that this is not end here. They are the continuous diagram. Okay, top. Okay, they are the continuous diagram. Okay, and this in that direction. All direction are possible here. Okay, all direction are possible, and each corner of that crystal we have some silicon. There is some silicon is look like, and this line is represent the covalent bond. Okay, and this diagram is look like there is a covalent bond. Okay, these are a covalent bond. They are not end here, they goes upward in that direction. These are not end. They actually this diagram is not end here, the continuous. They are continuous, say that. Okay, all direction. So these are the standing, this stick, this arm or sides, these are the bond here, and this is a covalent bond, and that's a pure semiconductor. And silicon, germanium have some pure semiconductor. Okay, suppose if I draw a germanium diagram, band diagram, and silicon band diagram, both are the same. Okay, and suppose you draw the diagram, suppose silicon, and here the silicon, silicon. Okay, that's not in here. Here is a silicon also. Okay, the diagram is not in there. They're continuous diagram. They are continuous here in all direction. In all direction are continuous. Now, if you see that this stand is a bond. Okay, this is a covalent bond, and due to thermal agitation, if I say that temperature is now greater than 0 Kelvin, so due to thermally, due to actually this 2D diagram, not 3D diagram, try to draw it. This is a 2D diagram, and this diagram is 3D, and okay, that's a 2D diagram. And due to thermally change or thermally due to thermally, this bond is break. If the bond is break, now that electron are free. So if that electron move free here, electron goes negative charge here, and they create a vacant here. Okay, due to thermally, this electron move in here and create a backend here. Okay, and these electron now a free electron are free or also called a charge carrier. And here these electrons are in charge carrier and these are some minus. If that semiconductor if there is silicon lost electron and here this gap is filled by a plus charge and this plus charge is called gap. Okay, missing of electron is called holes. Okay, these are the free here the electron and the holes also a charge carrier. Here the electron is a charge carrier, there is the electron and holes also a charge carrier. Carrier. Okay, so here we see that a number of free charge carrier of electron, suppose say that is Ne, and if you say the number of holes charge carrier is Nh. Okay, and now that free electron strike the other and there is a process is continuation. Okay, if I the electron strike other, this electron now in free in that direction create a hole here, positive charge. Similar process continuously move in that direction, this electron in that direction. The process is continuation. Okay, so there the charge carrier, here the two types of charge carrier we get. There's a electron charge carrier is called a Ne and another charge carrier is a whole charge carrier, and this charge carrier is called intrinsic charge carrier. So Ne and Nh is called intrinsic charge carrier. Charge carrier. Because the semiconductor is the intrinsic semiconductor, pure semiconductor, the charge carrier also that intrinsic semiconductor charge carrier. So now we get that is Ne, that is also equal to Nh, both be the same. Okay, in pure semiconductor both be the same, and now that is also equal to Ni. Okay, and this Ni is called intrinsic carrier concentration. This Ni is called carrier concentration. Intrinsic carrier concentration. This is Ni. These all be the same. If there is a free charge carrier of electron, suppose I say that due to that free charge carrier we get some current, and this current is called electron current due to that electron, and here we get some current also, we get flow of hole. If a electron are flow, we get some current IE, electron current. We also get another current is called IH, hole current. So total current of semiconductor, so I total we get a electron current plus hole current for intrinsic semiconductor. Okay, and the process, here the process, okay, the process to generate a free electron, okay, is a called generation of conduction electron. The process generates free electron. These electrons are free electron because they are not free, they are not a part of any bond, they are free. Okay, and free charge or free electron charge. Okay, and this carrier is called generation of conduction electron. Charge carrier is called generation of conduction electron. Generation of conduction electron. Here the generation of conduction electron. Okay. Now simple this process also here. If see that and there is a hole. There is a hole. If I try to draw same diagram here, suppose there is a silicon. Suppose there is a silicon and say that is 1, 2, 3 and 4 and Another silicon, another silicon. There is a 4 electron here. And now that, okay, this process is continuous, okay, not in, okay. Now due to thermal agitation we lost, okay, we lost this electron, and this electron goes in that direction, suppose here, and this electron now in free, so create a hole here. Actually, now if you create a hole, so hole is a positive charge. Now another electron from any other band, they are now break. These electrons are filled here. Okay, this electron from these bands, suppose now these are hole here, and now these hole are moving in that direction. So electron in that direction are moving, so hole are moving in that direction. So these electron break the bond here and move here. Okay, so here hole with recombine. Okay, so here is a recombination, and that electron here, the electron recombine with holes. Here electron recombine with holes, and this process is called recombination. Recombination, that's very important. Here you see that this electron and on any other band of electron, they are now recombined. Here there is a hole, and this electron create a hole here, suppose a positive charge, create a hole here, and now this electron move here, so hole move here, there in that direction, and now electron moving perfectly their opposite direction. This is the electron moving. Okay, so here at equilibrium, here at equilibrium, number of electron and number of holes be the same for pure semiconductor obviously, but the rate of generation of electron, so rate of generation is equal to rate of recombination. Okay, at the equilibrium, that's the same. Rate of recombination is also equal to rate of generation. If the electron here, now similarly same electron are generated here. If I due to thermal agitation the bond is break, and now that electron are free here, so that's a generation, and now that electron recombined with another hole is called as a electron recombined with hole. There is some recombination here. So rate of generation also equal to rate of recombination at equilibrium. Now we jump into impure semiconductor. Okay, we know the concept of what is a pure semiconductor, and there is a free charge carrier electron, and there is a hole, and you know that is generation and what is recombination, and flow of electron, direction of electron, and direction of hole. That's very important. Here two charge carrier, we get some hole. Due to hole we get some current, hole current, and due to electron we get some electron current, and if I combine these two current we get a total semiconductor current. That's a pure semiconductor. Now jump into impure semiconductor or extrinsic semiconductor. Why this semiconductor is needed? Why the extrinsic semiconductor is needed? Because there is thermally generated sum of electron here. Okay, thermally. If a bond break, we get some charge carrier here due to thermal carrier. Actually, these are not controlled in our hand. Okay, this free charge carrier not controlled in our hand, but they depending on some other factors. But extrinsic semiconductor, they actually depending on our hand, because we need some impurity. We added some impurity to that semiconductor and create it artificially hole an electron. Okay, so that's the extrinsic semiconductor. So extrinsic semiconductor is the impure semiconductor. Semiconductor is an impure semiconductor. Okay, we added some impurity here. Main purpose, we added some impurity. and this impurity create extra electron and extra hole. Okay, and this process is called doping. Okay, doping. Suppose there is a two types of extrinsic semiconductor. First is a N-type semiconductor, other is a P-type semiconductor. So first we discuss what is a N-type extrinsic semiconductor. Due to name such as N, so means here is some electron. Okay, here we see that I say that a free charge carrier is called a Ne. Okay, so suppose that the N means stands towards the electron. Okay, so we added some pentavalent or last electron was 5. That type of atom we input in the pure semiconductor. Okay, suppose doping by pentavalent atom like phosphorus. Last electron number is 5. Okay, arsenic, antimony. So phosphorus. So here you see that a phosphorus here, and phosphorus have 5 electron in last cell, 3, 4, and suppose another, and surrounded by a silicon. 1, 2, 3, 4. Here is a silicon. 1, 2, 3, 4. Here is another silicon. 1, 2, 3, 4. Here is another 1, 2, 3, 4. And we see that the covalent bond. Here is another phosphorus. And here we see that, and here the extra electron. Okay, there you see that some extra 1 electron, and if I put here, you see that extra another 1 electron. You get an extra electron. Okay, and the process is a doping. Okay, this process is doping, and you get an extra 1 electron. Okay, and the atom, this phosphorus atom is called dopant. This is called dopant. Okay, and the phosphorus is a dopant. Phosphorus into the added here is called dopant. Okay, and here it create a donor impurities. These are donor impurity. So this N-type semiconductor is called donor impurities. Okay, finally we get some doped semiconductor, and finally get a doped semiconductor. Okay, so here we get some huge number of electron here. So here the two type of charge carrier, you know that is a electron and hole. Here we see that electron is a majority charge carrier. So here electron is majority charge carrier. And due to there is some temperature obviously greater than 0 Kelvin, due to thermal agitation they break some bond, and we get some minority charge carrier, minority carrier, and here the minority carrier is hole. So majority carrier is electron, and there is a minority carrier is hole. So number of charge carrier for electron here is greater than number of charge carrier of hole. So that's why this semiconductor is called N-type semiconductor. Okay, so because there is a majority charge carrier electron, minority charge carrier is hole. So mainly the current flow from this semiconductor depending on electron. Okay, and that semiconductor is called doped semiconductor. Some we added some impurities, so it's called donor impurities. Okay. Now we have another type of semiconductor is called P-type semiconductor. Okay, P-type semiconductor, or say that is hole type semiconductor. So here we added doped by a trivalent atom. suppose say that is aluminum. That last in electron number valency be the 3, and that here is the aluminum 1 2 sorry 3 electron surrounded by the silicon. Okay, and this is a covalent bond. This is a continuous, not end here, continuous. And here you see that extra hole here be generated. Okay, so hole be generated. So here dopant is a aluminum. So dopant is a aluminum, and here these call donor impurities. Okay, and here that acceptor impurities. Here we see that a acceptor impurities and acceptor atom, and these whole accept the electron is acceptor atom. Okay, acceptor atom, and say another name is acceptor impurities. Acceptor impurities. Impurities. Okay, and here previous case for n type the generation is very important. Okay, and here we see that mainly that is a recombination. So here hole is here, huge number of hole here, and due to thermal agitation the electron break here, move in that direction, create a hole in flow, and there is another hole, huge number of hole created. So hole is much greater than charge carrier of electron in for p-type semiconductor. Or here it is very important for due to main is a recombination. Okay, that's a p-type semiconductor. Is a majority charge carrier is a hole, minority with the electron. Okay, and it doped by some trivalent atom, and obviously these are the impure semiconductor. And for there is a p-type semiconductor, here is a dopant aluminum, and p-type semiconductor is a dopant with the aluminum or doped by trivalent atoms. Okay, and we get some extra hole here, so that the majority charge carries hole and minority with the electron. And for n-type semiconductor doped by some pentavalent atom, and dopant is a pentavalent atom, and for phosphorus arsenic. Okay, and you get some extra 1 electron. Okay, and this extra 1 electron means a extra charge carrier. So here the charge carrier with the electron. So majority charge carrier is electron and minority charge carrier is hole, because the temperature of more than 0 Kelvin, there's some bond break here. We get some very little bit amount of minority carrier. So minority carrier obviously present in the semiconductor. Okay, so that's the majority minority carrier. Okay, so here the majority carrier is high, here the minority carrier is low in both cases. Okay, here the electron is high, and here is whole number is high in p-type semiconductor. That's the basic about idea about the extrinsic semiconductor. Okay, so due to that impurities we get some extra energy level. Okay, so that extra energy level also change the band diagram, energy band diagram. That discussion in jump into the next classes. Okay, so today end the class here. If you have any doubt in the today's class, please ask in comment section. I will try to give the answer. Okay, so we meet again in our next class. Thank you.